Hey y'all, so I am going to do a quick review of the sample final that's on Canvas. So let's just get started. The first step is always to download your R data. So I'm just gonna download it, and it's in my downloads now. And then in our R, we click File, Open File, and go to your downloads, and just open that R data. And you'll hit yes for it to put it into the environment. All of the data that you'll need for this practice final shows up in your global environment, along with those two functions that we've used throughout the semester, the ci.prop and the ztest.p. So let's get started with question 1. A university offers only 2 degree programs, one in electrical engineering and one in English. This data is found in admissions.csv by program and gender of applicant. Compare the percentage of women admitted to each program out of the women that applied with the percentage of men that admitted to each program out of the men that applied. So in my opinion, the best way to visualize this admissions data, so if we click on the admissions data, there's gender, decision, and program. So I like to look at this in a 3-way table, and I put gender, decision, and program in the table. So I always do for all 3 of those. And when we run this, I get 2 little tables, one for engineering and one for English. And I see that females, 10 out of 20 were admitted, and males, 30 out of 60 were admitted. So that means 50% of women were admitted to engineering and 50% of men were admitted to engineering. So there's no difference in the admittance rate for engineering. Then we can look at the same for English. 10 out of 40 were admitted to English for women, and 5 out of 20 men were admitted to English. So that 10 out of 20, 25%, and 5 out of 20 is also 25% admittance to English. So there's no association between gender and admission decision. Gender is independent of admission decision because no matter what gender you are, it's the same chance that you'll get into each program. Question 2. A student at LASA High in Austin collected data using a Google form on the LASA 2016 Facebook page. The survey asked, how many times did you watch the Anaconda music video by Nicki Minaj? The data is in views.csv. And it says the view data is blank. So it's trying to figure out if it's symmetric or skewed. So the best way to visualize this is through a histogram. So I use the hist function, and I do my data name, which is views, and $ that column name, which is how many times did you watch the Anaconda music video. And I'm going to run that. And when we look at this plot, we see that there's a long tail on the right. So this is called skewed to the right. Question number 3. The attached dataset homeprice.csv contains the listed prices in thousands of dollars and the number of square feet for 94 homes in the Austin area. The data came from a website of an Austin realtor offering homes in the area for sale. Use the data to predict the listed price for a 2,300 square foot home. So we're trying to predict price given square foot. So the first thing we need to do for this question is create a linear model of price, and then our little squiggly or our tilde, and then our x. So remember the lm function is always the y variable, and then the tilde, and then the x variable. So I am calling this model 3, and I did the lm function of price predicted by, that's what that tilde means, square feet. So I'm going to run this model, and it made that model. And to look at the coefficients, you can either do summary of model 3, and it gives you a lot of different information, or just look at the coefficients. We can use this function called coef, which just shows me the coefficients of each one. And I see that the intercept is 50.59, and the coefficient of square feet is 0.16. So then I just plug my x, which is this 2,300 square foot, into this equation. So I do the intercept plus 2,300, the x, times the slope. And I see that the predicted price using this model is $417,000. Question 4. The attached dataset, homeprice.csv, contains the listed prices, so this in thousands of dollars, and the number of square feet for all of these houses. So this question is about that same dataset that question 3 was about. And it says, before using least squares regression for predicting price from home size, we should look at a residual plot. So we need to look at the residual plot for that model that we just created to make sure that the equal spread assumption is true. So there are 2 different ways to do this. Either way, you get the exact same plot. So the first, I'm going to plot my x values, which is the square feet, comma, my y values, which are the residuals of model 3. This function could be residuals or it's resid. There are 2 different functions in R and they do the exact same thing. Resid and residuals do the same thing. I'm going to do plot my x, comma, my y. And I see that this plot is a fan. It shows increasing spread, which basically means that as my home price, as the square foot of houses increase, this model is worse at predicting bigger square footage houses. So about a 4,000 square foot house, the model is not as good about predicting the price. Whereas a 1,000 square foot house, it's a lot better at predicting the price. Another way to get this exact same plot is to just use the plot model function. So I'm going to just plot model 3, and this shows me a lot of different plots. So see down here it says hit return to see next plot. I'm going to go down here and hit enter. And this first plot is the one that we care about. This is the exact same plot that we just saw before, except it has this line and it shows it fans out and it shows the outliers. So this is something that R does for you, and it gets the exact same plot. And it also shows increasing spread about the line. A thing to note is that if you hit enter again, it'll show you the normal QQ plot. And then you have to hit enter 2 more times. It shows you 2 plots that we don't use in this class. So don't worry about those last 2 plots. You only care about the first 2. And going back to the question, we see that prediction of listing price will be less accurate when the home size is larger because the residual plot shows increasing spread about the line. Means it's worse at predicting bigger houses. Question 5. 20% of homes in Austin have a fireplace. 64% of homes in Austin have a driveway. Of houses with driveways, 30% have a fireplace. What proportion of homes in Austin have both a fireplace and a driveway? So this is just knowing your probability rules. This is P of A and B equals P of A given B times P of B. So let me just substitute in what we're talking about. P of fireplace and driveway equals probability of fireplace given driveway times the probability of driveway. And all this information is given to you. Probability of fireplace given driveway is this sentence: of houses with driveways, 30% have a fireplace. Probability of driveway is this: 64% of homes in Austin have a driveway. So all you need to do is 0.3 times 0.64, and we get the proportion is 0.192. Question 6. Consider an investment opportunity with possible annual returns between 25% and negative 12%. The possible outcomes and probabilities are listed in the investment.csv file. The standard deviation is a measure of the risk of this particular investment. The value of the standard deviation is equal to blank. So if we look at this investment data set, we see that these returns are not equally weighted. Some of them are more likely than others. So that is why we cannot just do the standard deviation function, because these returns are not equally weighted. So we have to do that part of code in which we account for these are not equally weighted things. So the first thing I'm going to do is calculate the expected value, and it's basically doing the sum product of the returns times the probabilities. So I'm going to make a new vector, which is all of the returns times all of the probabilities. I'm just going to sum up that vector in order to find the expected value. So the expected return, what I just calculated, is 4.58%. Now we need to calculate the standard deviation, because that's what this question is asking for. So what I'm going to do is make a vector of the squared deviations, which is each return minus the mean I just found, squared. So that's why I call them the squared deviations. And then I'm going to multiply all of those squared deviations times their probabilities because they're weighted differently. That's the core part of this. They're weighted differently. And then I calculate the variance by adding up all of those weighted deviations. And then I just square root the variance to find the standard deviation. And it's 10.009. So this portion of code, you should go through these steps every time you need to do a standard deviation with things that are not equally weighted. Question 7. Down 2 points with almost no time left on the clock, Shaquille O'Neal is forced to heave a three-pointer as time expires and is fouled in the process. O'Neal, with a career free throw percentage made of 52.8%, will now receive 3 free throws with a chance to tie the game or win. What's the probability that he does so by making at least 2 out of his 3 free throws? Assume O'Neal makes each free throw independently with the same probability of 52.8%. So there are a couple different ways to do this question. I'm just showing you the way I do it, and I use the p-binom function. So we're looking for the probability, and basically what we do is we put in here the successes, the total number of trials, and the probability of success on each trial. So p-binom of 1, 3, 0.528 is the probability of making 1 or less free throw given 3 trials and a 52.8% chance of success on each one. Alternatively, because this question is asking the probability of making at least 2 out of his 3 free throws, I have to do 1 minus p-binom to find the probability of making 2 or more. And we see that that probability is 0.542. Question 8. The weight of a randomly selected can of a new soft drink is known to have a normal distribution with a mean of 8.3 and a standard deviation of 0.2. The weight that should be stamped on the can so that only 2% of cans are underweight is closest to blank. So we are given a probability in this question, and we are asked for the quantity or the weight. So this is big hint. We're going to use Q norm. It's a normal distribution. We're looking for quantity. And I'm going to put that probability first, which is that 2%. Then I put my mean, 8.3, and the standard deviation of 0.2. And we just run this, and we see that the value that should be stamped on the cans is 7.9 ounces. You were designing a survey about the City of Austin transportation system. Which of the following questions would be the best way to obtain clear data on bicycle use using unbiased wording? So this is just a conceptual question. We want the best survey question. So this first option, how many days a week do you help the environment by not emitting greenhouse gases? This, do you help the environment, is the hint. This is a biased question. The second option, how often do you ride your bike to work? Select from often, occasionally, and never. This is also not a good option because people have different definitions about often, occasionally, and never. A lot of people, it needs to be a quantitative option that is going to give people the exact amount. So B is not a good option because some people think often is every day, some people think often is once a week. How many days a week do you ride your bike in a lane intended for automobile traffic? This is also biased because of this intended for automobile traffic. So option D is the best option. It says, how many days a week do you use a bicycle to go from home to work? And this is going to give us a clear number answer. How many days a week do you use a bicycle to go from home to work? And it also doesn't have any bias in that question. Question 10. In 1995, the Gallup poll asked a sample of 620 people whether their support of baseball had been affected by the players' strike. 248 people in the sample said yes. If the Gallup poll had asked 1,500 people rather than 620 people, the margin of error would be blank. So this is another conceptual question, and it's about what is increasing sample size due to the margin of error. And I see that my margin of error is my z star times square root of p hat times q hat divided by n. So this is just our definition of margin of error. And we see that the margin of error inside of that formula, it's divided by the square root of n. So if I increase n from 620 to 1500, this is going to decrease the margin of error. So if I increase n, then my margin of error is going to go down. So that leaves us with this option, that the margin of error would be less because the sample is now larger. Question 11. A major credit card company's Platinum Card recently ended a benefit that enabled card members to access first-class airline lounges at many airports throughout the country. The CEO wants to know if this has decreased the percentage of customers that would rate the card's benefits as excellent. Before the loss of benefits, the percentage of customers that rated the card's benefits as excellent was 35%. A survey conducted after the loss of benefit of 700 Platinum Card users found that 33% of customers rated the benefits as excellent. So it says, what is the p-value for the following test? So I'm going to show you two different ways to do this. The first way is calculating the p-value by hand, and the second way is arguably the easier way, but you should still know how to do them both ways. So the first way, I'm going to set my sample size to 700, my p0 to 0.35, and my p hat to 0.33. And I calculate the standard deviation by doing the square root of p, then p null times 1 minus p divided by n. And then I do my p-value by putting in my p hat, my p null, and that standard deviation. So we're basically calculating the probability of seeing something as extreme as or more extreme than the sample, which is as extreme as 0.33 or more extreme than 0.33, given that the null, this 0.35, is true. So I'm going to calculate my p-value, and I see the p-value is 0.134. Alternatively, you can just use the z-test.p function, and I put in my p hat, I put in my n, and I put in my p null. And it gives you your three p-values, and you would just need to look at the lower one because we're testing that p is less than 0.35. And we see that that is the exact same number as we got earlier. So it's 0.134. Question number 12 is also conceptual. A random sample of n equals 100 adult American men is taken, in which the weight of each man is recorded. Suppose a 99% confidence interval for the mean weight of an American man is calculated to be 175 plus or minus 5.16 pounds, or 169.84 to 180.16. So it's about interpreting this confidence interval. So the important thing to remember is that confidence interval always looks for the true mean, the true proportion, the true slope of the line. It's not about the sample, and it's not about an individual point. So this confidence interval is going to be looking for the true mean. So this says 99% of adult men. This is talking about men individually. That's not right. And that also eliminates all of the above. B is the best answer because it says we have constructed an interval using a procedure that will include the true mean 99% of the time. D is also not right because it says if the sample were repeated many times, the average weight would be between 169.84 and 180.16. This is talking about a sample, not about the true population mean. So that's why B is the best answer. Suppose that measurements of a toxic chemical in wastewater from a mill vary over time according to a normal distribution with mean of 0.005 and standard deviation 0.0012. Measurements on 9 dates are taken and the sample mean is reported. If the sample mean is 0.006 or above, the mill will be required to pay a fine. what is the probability that they will have to pay the fine? So the key thing to remember in this question is we're talking about this sample. If the sample mean is 0.006 or above. So we have to remember that when we put this in p-norm, we can't just put the standard deviation of the population. We have to put the standard deviation of the sample. So we use our p-norm. We put the value we care about, this 0.06. And we put the standard deviation divided by the square root of n. And because it's saying if the sample mean is 0.006 or above, I have to do 1 minus because p-norm always shows me the lower tail, so I want it to do the opposite. So I'm doing 1 minus p-norm of that 0.006, the mean of 0.005, and the standard deviation of the sample, which is standard deviation of the population, divided by square root of n. And I see that this is 0.0062. Question 14. A government agency is concerned about deterioration of automobile anti-pollution equipment after cars are sold. The agency took a sample of 19 new cars at dealers, and a year later took a second sample of 18 cars that had been in service for at least 8 months. The nitrogen oxide readings are given in NOx.CSV. Carry out the test to see whether there is strong evidence that the means are different. So we're doing a t-test in this, and we're comparing two means. We're comparing NOx new and NOx used. So whenever we're doing a hypothesis test for two different samples, the two things to remember that you have to check is, are they paired or not? And is this one-sided or two-sided? So this data is not paired because it's not the same cars that are being tested. It's two complete different sets of cars. So they're not paired. So I didn't put paired equals false because this function defaults to paired equals false. So you don't have to put it. I didn't put it. It defaults to paired equals false. The other thing you need to check is whether it's one-sided or two-sided. And in this question, it said, carry out the test to see whether there is strong evidence that the means are different. So it just asks if they're different, so this is a two-sided test. So you could put alternative equals two.sided, but you don't have to because it defaults to two-sided, so I didn't put it. So I'm just going to run a t-test of new compared to used. The order doesn't matter between here. And we look at our p-value, which is right here, which is 0.01299. And this question is just a little bit off with the p-value, but it's close enough. Question 15. Two laboratory procedures for determining the amylase level in human body fluids are compared. The new method is less expensive than the standard method, but may give different results. Both methods are used on each of 10 subjects. This is the biggest hint. This is your hint that this data is paired because both methods are used on each of the 10 subjects. So there were 10 people. Each person got the new method and the standard method. So they're paired by each person. You may assume that the 10 subjects are a random sample from the population of interest and that the test results vary normally. Results in amylase.csv give the results from the standard method and the new method for each of the 10 subjects. The 95% confidence interval for the mean amount is closest to blank. So, my t-test function, we use the same one for confidence intervals. I put my new and my standard, and they are paired, so we have to put paired equals true. And for confidence intervals, you have to decide the confidence level. It defaults to 95%, so you don't have to put this. I'm just going to keep it in this line. Doesn't matter. But if it was 95% and 90%, you would have to change it. So we're going to run that t-test, and we see that our confidence interval is shown right here. It's 6.5 to 12.5. Question 16 is also a conceptual question. Insurance companies track life expectancy information to assist in determining the costs of life insurance policies. Last year, the average life expectancy of all policyholders was 77 years. ABI Insurance wants to determine their clients now have a longer life expectancy on average. So they randomly sample some of their recently paid policies. The insurance company will only change their premium structure if there is evidence that people who buy their policies are living longer than before. Which of the following statements is true about this hypothesis test? So first, let's talk about whether it's talking about a mean or a proportion. So the big hint, there's a couple hints in here. It says the average life expectancy. It says they want to know if their clients now have a longer life expectancy on average. And so those are our two main hints that this is about the mean life expectancy. So we can cross out the ones about the proportions. The next thing to see is whether this is one-tailed or two-tailed. So it says the insurance company will only change their premium structure if there's evidence that people who buy their policies are living longer than before. So we're only checking if that average life expectancy has increased. So that makes this a one-tailed test about a mean. Question 17. A sales manager was interested in determining if there is a relationship between college GPA and sales performance among salespeople hired within the last year. A sample of recently hired salespeople was selected. The number of units each sold and the number of units sold last month was recorded. Relevant data appear in the attached file. Are the assumptions or conditions for regression inference satisfied? So let's go through all of these assumptions one by one. So, equal spread. That's where you use a residual plot. Linearity, we just use a regular plot. Independence, we usually just assume it from the question that these two things are independent. And nearly normal, we can look at a QQ plot, or we can look at the histogram of the residuals. So first, let's check linearity. Just going to plot GPA versus units sold. So I always put my X first and my Y second in the plot function. So X comma Y. And let's look at this. It looks quite linear. Straight line on there. So the linearity condition is satisfied. That's all good. So now we're going to check the equal spread with our residual plot. And we talked about this a little bit earlier. First, I'm going to create a model with the LM function with my Y variable, and then the tilde, and then my X variable. I'm going to create that model. Then I can just do plot of model 17. I don't really have to have line 113. I'll just delete that. Actually, excuse me, yes I do, because I'm going to use that as the residuals. So I'm going to create a little vector called the residuals, and then I'm going to plot model 17. And this is actually going to help me check the equal spread first. So this is our residuals versus the X values. And this looks like a pretty good cloud, so there's no trend in that one. And then I can check the QQ norm, which is that nearly normal condition, right in that next plot R does just for me. And this looks quite straight. So my QQ plot and my histogram of residuals are both good. So that checked the equal spread condition and the nearly normal condition. Alternatively, you could use the histogram of the residuals instead of that normal QQ plot. And excuse me, you have to get through all of those plots. Now let's rerun histogram of residuals. And this looks nearly normal. So all of our conditions are satisfied, and we are also assuming that college GPA and sales performance are independent. So all of the required conditions are satisfied. Your college GPA usually doesn't affect your sales as a salesperson. Question 18. On a typical night in New York, about 25,000 people attend a Broadway show, paying an average price of more than $75 a ticket. The attached data gives data about shows in Broadway for 78 weeks from 2006 to 2008. So it gives us all these different variables. And it says, use regression to model receipts in terms of the other variables. The coefficient for paid attendance tells us how much receipts change if the total paid attendance changes. Give a 95% confidence interval for this coefficient. So I'm going to create a model of receipts in terms of the other variables. So I put my Y, which is the receipts first, and then I put my squiggly, the tilde, and I put those other variables. I put paid attendance, and then I put plus shows, and then plus average ticket price. So I'm just those three x variables are tacked onto the end of that function. So I'm going to run it to create model 18. And I can run summary to see all of these estimates. So it says we're looking at the coefficient of paid attendance. And this is the coefficient of that paid attendance. And also, if you don't like scientific notation, I like to look at it without scientific notation. You can do options SciPen equals 999 to get rid of that scientific notation. And we can see that the paid attendance coefficient is about 0.07. So the easiest way to get confidence intervals for these coefficients is this confint function. And we put a linear model inside it. So I'm going to say confident in model 18, and it shows me the 95% confidence interval for those ticket prices because it defaults to 95%. And I see this lower bound is 0.075, and the upper bound is 0.077. Question 19. This is about that exact same data set, so I won't read the whole question again. It says, use regression to model receipts in terms of other variables. We just did that in question 18. Based on your results, which variables do not have a statistically significant relationship with receipts? So you can use this same model that you created in question 18. I just copied and pasted that exact same line of code, modeling receipts in terms of those three other variables. So I just copied and pasted the exact same line right here. And we're looking for these p-values to see which variables have a statistically significant relationship. So we're going to look at summary of model 19. And these are my p-values. And I see that the one with the highest p-value, the one that does not have a statistically significant relationship with receipts, is shows, because it is greater than 0.05. All the other ones are very, very small. Question 20. A paint supply store wanted to know if the correct amount of paint was contained in 1 gallon cans purchased from a nationally known manufacturer. It is known from the manufacturer's specifications that the standard deviation of the amount of paint is equal to 0.02 gallons. A random sample of 50 gallons is selected. The supply store plans to test whether the mean is 1 versus it's not 1 at the 0.05 level significance. If the average amount in each can is really 0.99 gallons, the power of the test is 0.97. If the average amount in the paint cans is 0.99, then the probability of failing to reject the null hypothesis is equal to blank. So this is a conceptual question, and it's basically about knowing the definition of power. So the definition of power is the probability of correctly rejecting the null. So, if the average amount in each can is 0.97, the probability of correctly rejecting, which is doing good, is 0.97. This question is asking about the probability of failing to reject the null, which is the opposite of power. So the key thing to note is the probability of failing to reject the null is 1 minus the power, which is 1 minus 0.97. So the probability of failing to reject the null is 0.03. So it's just knowing that definition of power. Question number 21. Many students entering McCombs as freshmen have already earned college credits by passing AP tests and or taking dual credit courses in high school. 20% of freshmen enter with credit for first semester calculus. 12% of freshmen enter with credit for first semester stats. 3% of freshmen enter with first semester credit for both calculus and statistics. Let C be the event that a randomly selected freshman has credit for calculus. Let S be the event that they have credit for stats. Are they independent? Are they disjoint? So first, let's talk about what disjoint means. Disjoint means that if you are one, you cannot be the other. So in this case, disjoint would mean if you have credit for calculus, you cannot have credit for statistics. And we know that this is false. We know they're not disjoint because some people have credit for both. 3% of freshmen have credit for both calculus and stats. So there's no way they can be disjoint. Now let's talk about what independence means. Independence means that the probabilities of calculus times the probability of stats should equal the actual probability of both. So this 20% of freshmen entering with credit for calculus times this 12% of freshmen entering with credit for statistics should equal the true probability of both. So 0.2 times 0.12 is 0.02. So if they were independent, the proportion of students with both would be 2.4%. But the actual probability of both is 3%. So this shows that calculus and stats are not independent. So they are not independent and they are not disjoint. Question 22. In the college's dataset, create a regression model that predicts graduation rate from student-faculty ratio and combined SAT scores. Find and interpret the slope coefficients in this model. So I'm just going to make a linear model. I'm going to predict graduation rate from these two variables, average combined SAT and student-faculty ratio. So I've created this linear model. And then we just look at the summary, or you could also just look at the coefficients, coef function. Either one will give you the information. And I see that the coefficient for SAT is this 0.084. So the slope for the average SAT tells us that the graduation rate goes up, because that coefficient is positive, by 0.08 for each 1 point increase in the SAT. Now let's look at the student-faculty ratio. The graduation rate goes down for each additional by 0.73 for each additional student per faculty member. That was just being able to create a linear model and interpret the results. Question 23. The return of the SPY ETF should theoretically have the following relationship with the return of the S&P 500 index. I want to use the past year of data to test whether the slope is equal to 1. I run a regression of the return of SPY ETF on the return of the S&P 500 index. The output below shows the regression slope is 0.997 and its standard error is 0.003549. What's the test statistic for the test? So, the key thing to remember here is the definition of test statistic. It's sample mean, which is the 0.997 minus the null divided by the standard error. And I've told y'all before that this t-value is the test statistic. But this is the test statistic assuming that our null is equal to 0. In this question, it's a little bit different because we are testing whether the slope is equal to 1. So this t-value tests whether the slope is equal to 0. So that is not the t-value used. We have to plug it in with the null mean of 1. So I put my sample, 0.997, divided minus 1 divided by the standard error. And I get that the test statistic is negative 0.845. And if you're wondering where they got this 280.936, let's look at it. It's testing the null equal to 0. So if I change this null equal to 0, that's where I get this 280. That's not the test statistic that we care about in this question. We're testing whether the slope is equal to 1. So that's why is what you need to do. Question number 24, another definition question. When making predictions using a least squares regression line, y hat equals beta 0 plus beta 1x that had been determined from a set of data, extrapolation occurs if. So it's just knowing the definition of extrapolation, and that's just when we predict a value of y from a given value of x, even though the data has no x values that are nearby. That's just the definition of extrapolation. Question number 25. An operations manager was interested in determining if there's a relationship between the amount of training received by production line workers, the age of the worker, and the time it takes for them to troubleshoot a process problem. The number of hours in training received and the time it took for them to troubleshoot their last process were captured. The regression equation she obtained was blank. So, which of the following can be concluded based on this equation? So let's take this one step at a time. The first option. Hours of training and age are excellent predictors of troubleshooting time. Just from this equation, we have no idea whether they are excellent predictors of troubleshooting time. We were not given any error mechanisms. We weren't given a standard error number. We weren't given an R-squared number. So I cannot know whether they are good predictors just based from this equation. This question. Among workers of the same age, each additional hour of training reduces the predicted troubleshooting time by 0.3 minutes. That's perfectly good. When we're interpreting multiple regression, it's super important to say holding other things constant. So holding age constant, or among workers of the same age, each additional hour of training reduces the predicted troubleshooting time by 0.3 minutes. Perfect. The number 2.4 does not have a meaningful interpretation. Also very true. So the intercept is basically among workers with 0 hours of training and that are 0 years old, it would take them 2.4 minutes. That does not make any sense because you would not have a worker that is 0 years old. So that's why the intercept does not have a meaningful interpretation. Last option. A worker that is a year older is predicted to spend an additional 0.04 minutes of troubleshooting time. This is also wrong because it does not include that key phrase about holding other things constant. This would be right if it said, among workers with the same amount of training, a worker that is a year older is predicted to spend an additional 0.04 minutes of troubleshooting time. But it does not include that key phrase about keeping other things constant, so it is wrong. Question number 26, our last question. You want to estimate the average age of all Boeing 737 airplanes now in active domestic U.S. confident. This question is kind of weird. And you want your estimate to be within 1 year of the actual figure. The standard deviation of the age of these planes in service in the U.S. taken from another study was about 4.9 years. How large of a sample should you take? So we're using the formula for N, and this formula is directly off of the session 20 slide deck that's in Canvas. And it's the N equals 2 times sigma divided by margin of error squared. So I'm just going to plug in 2 times sigma, which is 4.9, divided by margin of error, which is, I want it to be within 1 year. So that's where I got the 1. I'm just going to square it. And I see that that's 96.04, and we always round completely up with sample size because I need greater than 96 people in order to have a sample that has a margin of error of 1 year. And that is all for the sample final. I am hosting a review session on Tuesday with the other TAs. And please email us and let us know if you have any other questions, and I will upload this to Canvas along with my script.